Hello everyone, thanks for your interest. My name is Sourabh and this is the poster presentation for our paper See, Think, Learn, a self-taught multimodal reasoner, accepted at WACV 2026. So starting with the motivation of our work, multimodal reasoning has demonstrated exceptional performance in vision language models, but enabling VLM with multimodal reasoning requires high quality chain of thought dataset, which is often obtained via labor-intensive human annotations or costly inferences from proprietary models. Self-training algorithm presents a promising alternative for the same by bootstrapping the high-quality security dataset from the open source VLM itself, whose reasoning has to be enhanced. But the problem with the current self-training algorithm is that they often neglect the perception component of multimodal reasoning. Further, in our analysis, we found out that the popular augmentation strategy, positive rationalization, which is introduced by STAR, causes shortcut learning. So, in order to eradicate these limitations, we propose a novel self-training framework, See, Think, Learn, in short STL, for VLMs. STL at its core uses a structured rational prompt, which grounds the reasoning based on the visual details present in the image. Further, following ST, the model iteratively generates and learns from its own structured rational, thus jointly improving both perception as well as reasoning. Further, we introduce negative rationalization, a new augmentation strategy, aims to enhance the discriminative ability and robustness of the model. As you can see from the qualitative figure, rational generated from popular self-learning frameworks such as STAR and R3V are very short, less detailed, and often miss the visual details present in the image. While in our case, the rationals are structured, more detailed, and you can see the reasoning part is very much grounded in visual details highlighted in the caption. Now coming to the method part. So as I have told you, our algorithm or our STL framework uses a structured rational prompt which encourages the model to output its response in a structured format having three components: caption, giving a detailed description of the image, followed by reasoning, giving a detailed thought process to answer the question, and grounded in visual details highlighted by the caption, and lastly, conclusion, which gives the final answer based on the reasoning. Now, from the figure, you can see the overall flow and architecture of our self-training framework. So we start with a MCQ VQ dataset having images, and based on each image, there is one MCQ question with multiple choices and a single correct answer. We prompt the model with the image and a question through a positive rational prompt, which is nothing but the structured rational prompt, uh, asking the model to generate responses in the form of that structured rational prompt. The model generates caption, reasoning, conclusion in its response, and we match the conclusion part with the actual correct answer present in the MCQ VQ dataset. If the ground truth answer matches with the conclusion, then we say that the rational is of very high quality. This is because if some error comes in the rational generation process, so suppose there are some errors which came in caption, then this error will be propagated to reasoning as well as to conclusion, and therefore giving incorrect answer. So if the answer is correct, then it means that the entire rational generation flow has been correct. So the rational is having good quality. We include this good quality rational into our rational trend set under the name of positive rational. Then, since in the first and only the model is able to give a good rational, then we say that the model is having a very good understanding of image and the question. We can leverage this good understanding to further augment our rational trend set by by negative rationals. So what we do is, for the samples which have went correct in the first turn, we again prompt the model asking it to explain why the other alternative choices are not correct. So here you can see there are four choices A, B, C, D, out of which A is correct and correctly predicted by the model in the first turn. We now ask the model with the same sample why the other choices B, C, D each are incorrect. This is done through a negative rational prompt which encourages the model to output its rational in the form of caption followed by explanation. Then we include these negative rationals into our rational trend set, and we finally fine tune the base VLM on the rational train set. After fine tuning, we get a fine tuned model which is having better reasoning, perception, and discriminative ability as compared to the base model. Now, from this newly fine tuned model, we again generate the rational train set. And this time, the newly generated rational train set is having better quality of samples as compared to the samples which are present in previous iteration rational train set. So, through this, we are getting better and better model and also better and better rational train set. So model progressively enhances both its perceptual grounding and reasoning capabilities through our STL framework. Then most important component of our STL framework is negative rationalization. The motivation for negative rationalization comes from human only. when we human try to solve an MCQ problem, we do not directly jump to find the correct answer. We basically go through all the choices present in the question, and then we filter out which choices are correct, which choices are incorrect, which choices are not possible, and then we say, okay, this answer seems correct. So this is how we as a human try to solve an MCQ problem, and we want to induce the same human strategy of discriminative learning and reflective learning into our framework, and we do it through our negative rationals. Now, this figure illustrates how our STL framework is different from STAR. So basically, uh, STAR has been originally proposed for LLMs, and we have extended for VLMs. So under STAR, we prompt the model with image in a question, asking it to generate a detailed thought process followed by the answer based on that thought process to correctly answer the question. Now, since the rational is having both the visual details as well as the detailed thought process combined inside it, so many times it becomes somewhat complicated and the rational appears noisy. Suppose in the first run, the model is not able to answer it correctly and given an incorrect answer for the sample. Then star employs a positive rationalization part. What it does is it takes all the samples which are went incorrect in the first run, and it again asks the model to give reasoning and conclusion, but this time providing correct answer as a hint to the model. Now, since the model has seen the correct answer as a hint, what it tries to do, it tries to generate a very vague and noisy reasoning, but the final conclusion correct. So, since the final answer is correct, the reasoning is included or the rational is included into the rational train set for star. And when we repeatedly fine tune the model iteration by iteration on such noisy samples, then the model learns to shortcut the reasoning. So what it does is it learns to basically generate a vague or noisy reasoning, but the final conclusion is correct. So this will eventually collapse the self-training framework. Unlike what we do is, firstly, we produce a structured rational. So the reasoning part is grounded in visual details highlighted by the caption. And further, we employ negative rationalization only for those samples which are went correct in the first run. So through this, we maintain the high quality rationals across all iterations of our STL run. Now comes the quantitative results. So we have performed our experiments on M3 core domain splits. We have taken 4 domain splits: common sense, language science, natural science, and social science. And across all the experiments, the base VLM employed is Lava 7 billion instruct. So in first table, we have compared our STL framework with several baselines. For zero-shot baselines, you can see prompting the model to reason before answer. The accuracy obtained is quite lower as compared to what accuracy we get from prompting the model to directly answer the question. This is because of the fact that the reasoning capability of the base VLM is weak. So when it is prompted to reason before answer, it falls short and it generates a noisy reasoning, and therefore based on the noisy reasoning, the final answer is incorrect, and it can be seen from the lower accuracy obtained in the table scores. And then if you fine tune the model only on the ground truth answer, which is what we call direct deceptive, then there is some improvement. But a great or superior improvement is obtained if we train the model on reasoning. So for that, we have employed self-training methods. We have compared our STL framework with 2 self-training methods, STAR and R3V. STAR is the first self-training algorithm, and R3V is the most popular recent self-training algorithm specifically designed and analyzed for VLMs. As you can see from the figure, STL outperforms all baseline and thus marking a significant contribution in the field of self-training frameworks. We have also presented an ablation study highlighting the importance of 2 of our components, which are structured rational prompt and negative rationalization. So without both, the results are suboptimal. When we include structured rational prompt uh, into our framework, then the results are quite good. This is because of the fact that now the reasoning is grounded in visual details highlighted by the caption, and also during fine tuning, we fine tune on rationals. So the rational has both caption as well as reasoning component, and thus we tune on both these components, thus improving models perception as well as reasoning capabilities. Further, if we include negative rational also, then the results are superior, and this is what our STL framework is. We further present an subjective analysis. We ask the annotators to select their preferred rational out of 2 rationals, one generated from star and one generated from STL for a given samples. These rationals we present as anonymized, And from the chart, it is evident that across all domains, annotators tend to prefer our generated rational more as compared to that generated from star, so suggesting that our rationals are having very good quality as compared to star. So this is all from my side. Please check out our code base on GitHub. And if you have any query, please feel to reach out to me or any of my co-authors from the contact details mentioned here. Thank you.